I'm Stephen Edwards, and I'm going to tell you about some of the details of the hardware of the Apple II, one of the early successful home computers. Let me start by saying I'm standing on the shoulders of giants here. The Apple II has been fantastically well documented, in part by Apple Computer itself in the form of the Technical Reference Manual, which was really polished by the 1979 edition. Two other amazing books, which both came out in 1983, each present the details of the Apple II hardware in incredible detail. Winston Gaylor's Apple II Circuit Description and James Sather's Understanding the Apple II. I've drawn liberally from both books. Most of the technical drawings I show are from them. Another classic is Don Worth and Peter Lechner's Beneath Apple DOS from 1981. While it focuses mostly on software, its low-level description of how bits are encoded on the Apple II floppies is excellent. The Apple II was released in June 1977, which you should be able to guess by looking at this early ad in Byte magazine. Clear the kitchen table, bring in the color TV, plug in your new Apple II, and connect any standard cassette recorder player. From the beginning, its ability to display color images was a major selling point, even though it initially shipped with only 4K of memory. Not surprisingly, the best way to understand the internals of the Apple II is to understand its video capability, since virtually every aspect of its design was motivated by video. First, let's talk about what video was like in 1977. From the ad, it's clear that you were expected to bring your color TV into the kitchen and hook it up to your Apple II, so let's talk about how that color television works. Analog video encodes images as an electrical waveform. At each point in time, the height of the wave tells us how bright the image is at that point. The most important thing is that images are scanned in raster order. We start looking at a tiny region in the upper left corner, then proceed horizontally to the right. At the end of the first line, we go back to the left and start again, slightly lower than we were before, just like reading a book. We can reconstruct the image by turning the waveform back into a series of light and dark regions. It's important to carefully follow the same raster path we did when we scanned the image. If we scan hundreds of horizontal lines, we get a realistic-looking image. If we update the image 60 times a second, we get the illusion of smooth movement. In 1977, the cathode ray tube, or CRT, was the dominant display technology. You may remember these as TVs. A CRT is a vacuum tube with a large, flat face leading to a thin neck. At the end of the neck is an electron gun where a heated cathode emits electrons into the vacuum. An anode charged to tens of thousands of volts attracts the electrons and sends a beam of them flying towards the face, which is covered in phosphor, a substance that emits light when bombarded with electrons. The strength of the electron beam is controlled electrically by the image waveform we talked about earlier. Electromagnets placed around the neck deflect the beam. These electromagnets are called the yoke. The television uses these to smoothly sweep the beam across the face of the CRT. A television uses two sets of magnets, one for vertical deflection and one for horizontal. By sweeping the electron beam across the face following the raster path and controlling its brightness, the image can be reconstructed. Do this fast enough, the image will appear to move. Now we can start to talk about video in the Apple II. The Apple II has 3 video modes. Everything is derived from the 40-character by 24-line text mode. Text mode characters are 5 pixels wide, 7 pixels high, and are displayed in a 7 by 8 pixel grid. 8 pixels high is a natural choice because 5 by 7 characters are attractive looking and because it's a power of 2. 7 pixels across will turn out to be both brilliant and very awkward. Each of the 64 possible characters is represented with a single byte in memory. The extra 2 bits control 2 character attributes, inverse and flashing. 40 times 24 is 960, a little shy of 1K. Here's the complete character set. Flashing characters were used for the cursor and to annoy your family members. The original Apple IIs only supported uppercase. Lowercase arrived in 1983 with the Apple IIe. Remember that televisions scan in raster order so that to display a character, the Apple II has to provide a waveform for each row of the character. Here's how Gaylor illustrates it. For the second row of an A, the first 2 pixels are black, then white, black, white, and finally 2 more black pixels to complete a 7 pixel wide row for the character. The desired waveform has 2 humps corresponding to the 2 white pixels. Here's Gaylor's block diagram of the circuitry used for text mode. The byte for the character, say an A, arrives encoded on 8 wires on the left, along with VA, VB, and VC, which tell us which row to display. These addresses are fed into character generator ROM A5, which generates 5 pixel brightness values for the row of the character. These 5 pixels are fed into shift register A3, which spits them out in order through the serial out signal. If you looked here, you would see the waveform for the character. This waveform is fed into exclusive OR gate B2, which may invert all the pixels to give inverse or flashing characters. Then into multiplexer A9, which selects among text, low-res, and high-res graphics, and then is eventually fed out through transistor Q3 to the television set. Low resolution or low-res mode follows naturally from text mode. Each character is split horizontally into 2 rectangles, and each rectangle can display one of 16 colors. The top rectangle's color is selected by the lower 4 bits of each byte, and the bottom by the top 4 bits. While low-res mode can cover the whole screen, the Apple II has the ability to display 4 lines of text at the bottom, which is very useful when you are coding or if you want to display some text along with the graphics. Low-res mode uses the same memory as the text mode, so when you switch back to text without clearing the screen, you see the graphical image coded in annoyingly flashing characters. Now here's perhaps Woz's greatest trick. He generates the waveforms for color graphics in almost exactly the same way he does for text characters. To see this, let's look carefully at this low-res color image. By itself, it's colorful, but not especially instructive. But let's try switching to a black and white television. The colored regions turn into a bunch of closely spaced vertical lines. If we look more closely, we see that the image is still fundamentally digital. That is, everything is either black or white. There is no gray, although regions that have more white pixels appear as brighter colors. This is not an artifact of the emulator I used to capture these images, but is an accurate reflection of how the Apple II generates video. Woz's basic trick was to generate these vertical lines at the so-called color burst frequency, which tricks a color television into thinking they represent colors. His technique was so bizarre that he got a patent on it, which I'll now explain. But first, no, we're not experiencing technical difficulties. It turns out if you can understand this test pattern, it helps you understand video on the Apple II. The waveform for one line of these color bars looks like this. If you looked closely at the blue regions, you see they were high-frequency sine waves, around 3.6 megahertz. So the first clue is that white is a flat line, and solid colors are rapidly oscillating signals. Another clue comes if we look at the color bars in black and white only. Here, the brightness decreases smoothly from left to right, just as the average of the waveform does. The brightness, or luminance, of the image, regardless of color, is effectively the average of these oscillations. We need 2 more numbers to characterize colors. The amplitude of the oscillating waveform indicates the saturation of the color. White, black, and grays all have low saturation. Bright red, blue, green, yellow, purple, cyan, or any other pure color has high saturation. In the color bars, the yellow is slightly less saturated than the others, so it looks a little whiter than the others, but the effect is subtle. The final thing we need is the hue of the color. This is whether it is red, blue, green, or some other angle on the color wheel. Here's the color wheel North American televisions use. Note that the saturation goes from high at the boundary to low near the center in this drawing. The hue is encoded in the phase of the oscillations, that is, how well they match up with the television's internal oscillator, which runs at the same speed as the color oscillations. As you might imagine, it's important to get the television to agree with the broadcaster about the phase of these oscillations. To do this, a color burst signal is sent at the beginning of each line of video, but off screen so you generally can't see it. Now you can understand Woz's color trick. The Apple II video circuitry runs at about 14.3 megahertz, which Woz chose to be exactly 4 times the color burst frequency. So if the Apple II outputs a digital waveform with period 4, the TV will interpret the waveform as color and display it as such. This is exactly what happens in the low-res mode. Here's Gaylor's block diagram of it. Again, 8 data bits arrive on the left from memory. These are the same bits that are delivered when the screen is in text mode, but this time they're treated as 2 4-bit colors, one for the upper rectangle and one for the lower. These 2 4-bit numbers are fed into 2 4-bit shift registers that send the 4 bits out serially to the multiplexer A9, which decides whether to display the waveform for the top rectangle or the bottom one. As in text mode, the output of MUX A9 is fed through Q3 and out to the television. Let's look at Gaylor's illustration for the waveform of one specific low-res color. Low-res color 2 is dark blue. In binary, 2 is represented as a single 1-bit. When fed out repeatedly through a shift register, it generates this waveform, which is high 25% of the time and low 75%. Since luminance is encoded as an average of the waveform, this waveform has a low average, so it will appear dark. Furthermore, this is a digital waveform, so its amplitude is large, so the color will appear saturated. Finally, look at the waveform for blue compared to that of the color burst signal. There's a 180-degree phase delay, which gives it a blue hue. Now consider low-res color 6, usually called medium blue. In binary, 6 is two 1s in a row, so we get a 50% duty cycle waveform with a slightly longer phase delay. It still looks blue, but the luminance is higher because the average of the waveform is higher, and the color is more cyan-like than deep blue. Light blue is low-res color 7, which in binary is three 1s. Moreover, the central 1 is in the same place as the lone 1 in color 2, so the TV interprets this color as having the same hue as dark blue. However, this waveform's duty cycle is 75% rather than 25%, so the luminance is higher and the color appears lighter. Here's the full collection of low-res colors, which I've arranged according to increasing luminance. Black is all zeros. Magenta, dark blue, dark green, and brown are each encoded with a single 1-bit, so they appear dark with low luminance. Purple, medium blue, green, and orange each have two adjacent ones. They have higher luminance, but slightly different hues than the first group. There are two gray colors, which arises from feeding the TV every other bit. This produces a waveform at twice the color burst frequency. The TV just gives up trying to guess the phase of this waveform and treats it as having no saturation, in other words, gray. The next group of colors each have three 1s. These are complementary to the dark group. They have the same hues and saturation, but have much higher luminance. Finally, white is color 15, which is all 1s. This doesn't produce a changing waveform, so it's not interpreted as a color, just high luminance. In other words, white. There's one other subtlety in low-res mode. Remember that there are 7 text mode pixels per character, but that the color burst signal is half this speed. This means that even and odd-numbered columns are 180 degrees out of phase from each other. While Woz could have fixed this in software by insisting you use color 1 in even columns and color 4 in odd columns, he fixed it in hardware by generating different waveforms for even and odd bytes. Here's how Gaylor illustrates it. For low-res color 6, medium blue, Woz outputs 0110, for even columns, and 1001, 1001 on the odd columns. To do this, he taps the circular shift register B4 in either the first or the third bit using multiplexer A9. Now let's talk about high-resolution mode, or high-res. High-res is also based on text mode, but uses 8 bytes per 7 by 8 pixel region instead of just 1. This provides individually addressable pixels, but consumes a lot of memory by 1977 standards, 8 kilobytes. The Apple II high-res mode can display 6 colors: purple, green, blue, orange, black, and white. The vertical resolution of high-res mode is 192, which is simply 24 times 8, but the horizontal resolution is complicated. There are 280 black and white pixels horizontally, but color requires 2 bits per pixel, so there are effectively 140 color pixels. Woz added high-res mode through a clever modification of his low-res circuitry. Here's Gaylor's block diagram of the high-res circuitry. In high-res, the two 4-bit shift registers used for low-res are configured as a single 7-bit shift register by data selector A8. The result is that for each 7-pixel text mode column, high-res mode again reads a byte from memory, but then shifts out the 7 bits individually rather than how low-res repeatedly emits the color in the top or bottom 4 bits. There's yet another subtle thing happening here. The color burst frequency is exactly half the text and high-res bit clock frequency of about 7 MHz. So using Woz's color trick, we should only get 2 colors in addition to black and white in high-res mode. But of course, Woz squeezed out 2 more. Interestingly, high-res on the very earliest Apple II motherboards only supported 4 colors. In the June 1979 edition of Byte magazine, Alan Watson III published an article discussing how color worked on the Apple II, to which Woz responded by showing how to extend the high-res color gamut by adding 2 chips. He did mention that adding this circuit voided the warranty. What Woz suggested adding in that article became a standard part of Apple IIs after then. In Gaylor's block diagram, this modification appears as flip-flop A11, which delays the waveform coming from the shift register by half a cycle. The otherwise unused most significant bit of each high-res byte selects whether this delay is inserted. If the flip-flop is bypassed, the byte can display green and violet. If the flip-flop is used, you get orange and blue. Unfortunately, unlike in low-res, bits are shifted out the same way in even and odd columns. The result is that code for, say, all green in an even column appears all violet in an odd column. This is fixed in software, of course, but adds yet another challenge for the Apple II programmer attempting to do fast high-res graphics. One side effect of these bizarre color rules is that you can't mix green and violet with blue and orange in the same byte. There were a few tricks to get around this issue. One was to stick to a single palette only. For example, here's Karateka, which uses only the blue-orange palette to great success. Another trick was to stick to black and white sprites against a colored background. Congo Bongo does this. Another fundamental trick Woz used in the Apple II was to run the memory at exactly twice the speed of the processor. Woz explains this in an article he wrote for the May 1977 issue of Byte magazine. A fundamental problem in any processor system with a video display is that both the processor and the video display need access to the memory. One solution was to let the processor step on the video, which is what Sinclair's bargain basement ZX80 computer did. Notice how the screen glitches every time the 8-bit guy presses a key. This is the processor taking over. Woz's solution was to interleave the processor and the video's access to memory. The video system gains access to memory in the first half of each processor cycle, and the processor gets the second half. This way, both processor and video have all the access to the memory they need. Today, such an approach would be an odd choice because processor speeds have greatly outstripped memory speeds. Modern computer video systems have their own dedicated memory that they allow the processor to access when they're not using it. The Apple II's 5¼ inch floppy drive, released in 1978, was crucial to its success. Woz credits it and VisiCalc for why the Apple II succeeded. By today's standards, Apple II floppies are primitive. They can only store 140 kilobytes, but for the time they were revolutionary, in no small part because they were relatively inexpensive due to Woz's clever engineering. For reference, here's the Shugart SA400 mini floppy, the standard one on which Woz based the Disk 2. Its analog board has about 19 chips. And here's the Disk 2. The drive mechanism is almost the same, but its analog board has only 4 chips. To understand how Woz did this, let's look at the details of how a floppy drive works. Mechanically, it's fairly simple. A spindle motor turns a spindle to which a circular disk is clamped. 300 RPM is typical for 5¼ inch floppies. The disk is covered with brownish magnetic material, and tiny regions of it can be selectively magnetized. A read-write head rides in circles around the disk. A stepper motor can precisely position the head a certain distance from the center to select which circle or track the head is on. The Apple II drives have 35 tracks spaced 48 per inch, so the head doesn't move far. The head can be made to write magnetic pulses on the track as the disk spins. These magnetic pulses stay in place until they're overwritten and can also be read through the head. Here's a top view of the Disk 2 drive. The spindle is the smaller circle near the center. The read-write head is under the black clamp on the right. The stepper motor is connected to the large white disk, which has an engraved spiral that positions the head. The spindle motor is in the upper right. Here's a close-up side view of the head against the recording surface. If you apply current to the head, it magnetizes the recording surface as shown by the arrows. If you reverse the right current, you reverse the direction of the magnetic flux on the disk. Later, when you are reading the disk and the head passes over one of these flux reversals, it induces a tiny voltage pulse that can be amplified and interpreted by a computer. The details of this process are subtle, and there's plenty of opportunity for error. But ultimately, if you record a square wave, each transition will become a flux reversal, and if you later pass the read head over them, the read electronics will turn the transitions into pulses. Woz also did a remarkable job reducing the number of chips on the disk controller card. For contrast, here's an S100 disk controller card from 1976 with 47 ICs that perform roughly the same function. Woz's card is so simple, I can tell you exactly what each chip does. PROM P5 contains the bootstrap code, which starts the drive, moves the head, reads the first sector from the first track, and jumps to it. In short, it's responsible for the sound you always hear when an Apple II starts up. That's the sound of the stepper motor pulling the head toward the outermost track by turning that spiral groove. The 9934 handles commands from the computer like turn on the drive and bring the head in one track. The 556 keeps the drive spinning for a little while after the computer asked it to stop, useful for sequences of disk operations. These two chips are glue logic that do things like make sure only one drive is on at once. Finally, these three chips are the brains of the outfit. Together, they convert between the drive's serial bit stream and the parallel data used by the computer. I think this, along with the color circuitry, are some of Woz's shrewdest creations. Writing to a floppy is comparatively simple. The main thing you have to do is spit out the bits from a byte one after the other and flip the output voltage when you see a 1. The one thing unusual about Woz's design is that it relies on a software timing loop. That is, the software on the processor is responsible for feeding the next byte to the drive exactly 32 processor cycles since the last. Reading is much more difficult. A central challenge is deciding when you've read a 0. Reading a 1 is easy. The readhead electronics delivers each 1 as a short pulse. But a 0 is the absence of a pulse during the time you might expect a 1. Although the speed at which data is written to the disk is controlled very precisely, the speed at which it is read varies because no two drives spin at exactly the same speed, and the disks are, well, floppy. So the read logic needs to be liberal about when it can declare it as read as 0. Here's how Woz's read sequencer works. First, it runs at twice the processor clock speed, or about 2 MHz. But the drive only transfers bits at 1/8 that speed, that is, at about 250 kilobits per second. Assume the sequencer starts in state 2 here. Now I'm going to draw the read waveform near the top of the screen and indicate the absence of a pulse with red. In state 2, the sequencer waits until it sees the first pulse in a byte. Red arrows are taken when there isn't a data pulse. Now let's assume it sees a pulse. This sends it to the next state. Green arrows are taken when there is a data pulse. These pulses are usually just 1 clock cycle long. Now, there shouldn't be another pulse for a few cycles, so the sequencer doesn't bother to check and just advances a few states. But starting in state 4, it starts checking for another pulse. Over the next 8 cycles, if it doesn't see a pulse, it simply waits and checks in the next cycle. After 9 cycles of not seeing any pulse, the sequencer decides a 0 followed the initial 1 and clears its input register, which I'm drawing here on the right. At this point, the sequencer starts to shift the 2 bits it knows about into the newly cleared register. First, it shifts the 1 corresponding to the first pulse we saw. The black 1 indicates the shifting operation. And then it shifts a 0, indicating the absence of the pulse after the first 1. Now let's go back and consider what happens if there was a second pulse. Typically, pulses occur every 8 cycles, which is 4 microseconds or 250 kilohertz. Let's assume a pulse did occur. A few cycles after the first pulse, the sequencer starts looking for a second pulse. If it sees one, it transitions down to this state, which is remembering that it just saw a second 1. Then it waits a couple of cycles, and again clears the register, shifts the leading 1 as before, but this time it shifts a second 1 since we saw a second pulse. At this point, the sequencer has seen 2 bits at the start of a byte, so it starts looking for the third. As before, it must wait a few more cycles before it can declare there wasn't a pulse, and therefore it saw a 0. But if there is still no pulse, it shifts a 0 into the register and starts looking for the next pulse. And the process repeats every 8 cycles. Now, if a pulse is seen during this process, the sequencer immediately knows it saw a 1 and stops looking. Here I've drawn the pulse the usual 8 cycles after the previous one, but it isn't always exactly here. The sequencer then waits for the pulse to go away, which should happen immediately, waits 2 cycles, and then shifts the 1 it just saw and starts looking for the next bit. There are a few other corner cases. If a pulse occurs while we're shifting 1, 0, we need to remember it and shift out 1, 0, 1. Similarly, if we saw 2 1s at the start of the byte, an early third pulse could interrupt us. Now, there's one other important case to consider. What happens when we see the last bit in a byte? By convention, the most significant bit of each byte written to the disk is 1. So if the most significant bit of the register is a 1, the byte is complete. This happens in two places. If the last bit is a 1, the sequencer transitions from the shift a 1 state back to the beginning like this. Similarly, if the last bit is a 0, the sequencer transitions from this state. Which brings us back to where we started, a state in which the current byte is valid and we're looking for the start of the next. All this cleverness around remembering the top 2 bits is to give the processor more time to realize a valid byte has been read. While all of this is going on, the processor is constantly asking the disk controller, do you have a byte? Do you have a byte? In any gray state, a valid byte is in the register for the processor to read. The complexity of what I've shown you here has mostly come from handling timing variations. There's one even bigger trick in reading a disk, synchronization. That is, figuring out where a byte sequence starts. As I've just shown you, if you start off waiting for the first pulse of a byte, this sequencer stays synchronized. But what if the processor starts reading in the middle of random bits? It turns out this sequencer will fairly quickly synchronize itself if you feed it a repeating sequence of 8 ones followed by 2 zeros. Credit where it's due, my animation of the sequencer comes from a drawing in Sather's book, which I adapted for this presentation. Another trick of Woz's was to improve the encoding of data on the disk. The standard at the time was frequency modulation, or FM, in which every other pulse on the disk represented a clock, limiting you to only 16 of the 256 possible 8-bit codes. This made it easier to separate the data bits from the clock bits, but wasted an enormous amount of space. Of course, you always need some clock bits, but Woz used an alternative known as group code encoding, or GCR. Here's Woz's code table. Every byte starts with a 1, and there can't be more than 2 zeros in a row. This is still limiting, but it allows 64 codes out of 256. This brought the capacity of Apple's single-sided, single-density 35-track floppy disks to 140K. The manufacturer, Shugart, only suggested 80K under FM. For comparison, the comparable Atari format could only store 80K. Commodore drives could store 170K and also use GCR, but required double-density diskettes and had a microprocessor in the drive. The Apple II motherboard has 3 rows of 8 dynamic RAM chips, which are inside the white rectangle near the center of the board. Revisions before about 1980 had memory select jumpers that would allow you to use either 4K chips or 16K chips. The first Apple IIs shipped with only a single row of 4K DRAMs, but as memory prices fell, most people upgraded. By 1980, the jumpers were removed and machines shipped with 3 rows of 16K chips for a total of 48K. In 1979, Apple released the Apple Pascal language system, which needed the Apple language card, which supplied an additional 16K of memory. Eventually, most Apple IIs acquired this card or a copy of it. There were many third-party manufacturers, including Microsoft. In 1983, Apple incorporated the function of the 16K card into the Apple IIe, since so much software, including ProDOS, had begun to rely on its presence. A 48K Apple II exhausted the 6502's 64K of addressable memory. Beyond the 48K of memory, another 12K was devoted to read-only memory for the System Monitor and AppleSoft Basic, and the remaining 4K was I/O locations. To increase the available RAM, the language card made its memory selectively appear in place of the onboard ROMs. Even more confusingly, rather than occlude the I/O region, the language card bank switched a 4K range of its memory. Another notable aspect of the Apple II 16K cards was how they were installed. Note the pigtail in the lower left corner of the card. To install a 16K card, you had to remove one of the DRAM chips on the motherboard, plug in the 16-pin jumper in its place, and then install the removed chip on the card. This was a trick to save hardware. While the multiplexed addresses needed by the DRAMs could be generated from the addresses on the slots, it was much cheaper to simply steal these signals directly from the existing DRAMs. Now I want to talk a little about the Apple II power supply. For comparison, here's the Commodore PET, which was also released in 1977 and also featured a 6502 processor. The PET used a much more traditional linear power supply, the primary component of which was the enormous massive transformer, the brown mass of iron on the left in this photo. Also notable was the enormous filter capacitor, the silver-blue cylinder in this photo. The Apple II's power supply was small and light by comparison. Inside the power supply, it is easy to see the difference. This is a so-called switching power supply, and while the technology was nowhere near as revolutionary as Steve Jobs would have you believe, it was unusual for the time. There's still a transformer, but it's vastly smaller than the one in the Commodore PET. There are also a handful of components on heat sinks and plenty of filter capacitors, but again, all are smaller than they are in the PET. Here's Gaylor's simplified schematic of the Apple II power supply, illustrating how a switching power supply works. Wall voltage is fed directly to bridge rectifier CR1, which converts the alternating current from the wall to direct current, which is then filtered by C1. Q3 is the heart of the switching power supply. It is the large trapezoidal thing with a silver circle in it near the transformer in this photo. Counterintuitively, Q3 is used to convert that hard-won DC back to AC, but there are good reasons to do this. The first trick is that Q3 generates AC at about 20 kilohertz instead of the 60 hertz that comes out of the wall. And this allows transformer TR1 to be much smaller because transformers are much more efficient at high frequencies. The second trick is that because Q3 is operated as a switch, it is much more efficient than the transistors used in the PET supply, which dissipate unwanted voltage as heat. The control circuitry varies Q3's duty cycle, which allows it to regulate the output voltage, again without wasting much energy. Volt-time light dimmers often worked on the same principle. Overall, Q3 generates high voltage, high frequency AC, transformer TR1 reduces it to low voltage AC, diodes like CR12 and CR14 rectify it into DC, and capacitors like C10 and C12 filter it. Like the transformer, filter capacitors like C10 can be smaller than their counterparts in the PET because they are filtering higher frequency AC. Complexity is the only drawback to such switching power supplies, but this was becoming less of an issue in 1977, and virtually every computer power supply works like this today. Thanks again for your attention. In putting together this video, I realized I have only scratched the surface of this marvelous home computer from the 1970s. There is a lot more to talk about. For example, see my other video on 6502 assembly programming, which shares more insights about the Apple II's video system, along with a lengthy discussion of the instruction set of the venerable 6502 processor at the core of the Apple II. I'll remind you again of some of my favorite technical references: the Apple II Reference Manual, Gaylor, Sather, and Worth and Lechner. And now, Bob Bishop's Apple Vision from 1978.
All right. That was great. There are a lot of interesting information in that video, Stephen. That was just really awesome. People here at the podcast studio we're just raving about it, and all the different details and different aspects, and the color part. Talking about the CRT, all the little tricks that Wozniak was doing. That was really a great video, and a lot of people are going to want to watch that again here. I've seen it, of course. I watched all the videos, but some of these guys didn't have a chance to watch all of them, so they're going to be happy to watch it again later. So, go ahead.
Yeah, it's definitely pretty dense. My goal was, yeah, you'll pick up something the first time you watch it, but there's two things. One, it's going to go on YouTube, and secondly, YouTube has this great speed feature where you can speed things up if they're boring or slow them down if they're overwhelming. I'm assuming the latter will be appropriate for mine.
Overwhelming, yes. So lots of good details. It shows that you're a computer science professor who really knows your stuff about vintage computers too. So, all right. So we have some questions. Stephen, do you want to start reading off?
Yeah. So somebody asked during the talk for some of the old. So most of that video was mine, but I did steal a bit of it. So the two things that I stole were a very nice video on CRT internals and so forth, and I've put something inside the Apple II, so it's on YouTube, and I put a credit on the bottom of the thing. But yeah, I did not do the animations of the CRT. I also stole that stuff from the 8-bit guy where he was demonstrating the glitchiness of the ZX80 or whatever it was. That was good. Let's see. Other people asked here. Let's see. Somebody was asking about the power supply. The PET had to drive the monitor. The Apple II didn't include that. That I don't believe that had much of an effect on the PET. The PET used, I believe, a pretty standard 12-volt monitor chassis that then reproduced all the high voltages off the rest of it. And I don't think the 12-volt load on it was all that substantial. So I don't know that it mattered all that much. Let's see. Yeah, I think I actually attached a small monitor like that to an Apple II at one point, and the switching power supply was able to handle it. So I don't think that was a huge example of that. Let's see. Somebody else commented during the talk that you could change the character ROM on the Apple II to give it lowercase. And yes, indeed. In fact, if you're really sharp-eyed, at one point, one of the later Apple II motherboards I was displaying there, if you notice, actually doesn't have the original ROM on it. That's my personal one that I bought from a guy quite literally in a dark alley in Brooklyn at one point. And they had put in the character ROM. So if you're really clever there, you can go and take a look and see that the character ROM is not original in that. But the operating system software didn't really know what to do with the lowercase characters for most of the time. Let's see. Did anybody else see any other questions coming up?
Chris, any questions? Any more?
Oh, I'm seeing.
Yeah,
I'm
the one that just came in.
Here. Yeah. So, was he far above engineers of his era? Somebody's asking about Woz. So, Woz's main skill, and that put him way ahead of the game of virtually everybody else, was taking stock parts and making them do stuff that you didn't think they were capable of doing. And his disk controller card with a whopping 8 ICs on it,
right,
is just insane. If you look at that, and it's just nuts. Now, in putting together this video, the thing that occurred to me, the thing that really separates the Apple II from the other personal computers of the era, was the absence of custom chips. The only custom chips on the board were the ROMs, and those kind of don't count. And you compare that with the Commodore 64, or the Atari, or any of the other things of that era, all of which had custom video chips. The fact that Woz got the video and the drive working with essentially no custom chips is just breathtaking. So yes, engineers back then were pretty smart at using limited resources. This, in fact, is always been the mark of good engineering. Woz was exceptional even by the standards of the day. Let's see. Somebody else commented also, the video design also gave dynamic RAM refresh for free. Plus it fit into the way the 6502 accessed memory. Yes, all of this is true. I didn't even mention the video refresh for the dynamic RAM chips. Some other people had looked at this presentation and said, oh, you left out this, you left out that, or whatever. Of course, I left out thousands of details about all of this. And so yes, the one drawback to the Apple II's construction is it was too cleverly integrated, and it didn't really take into account the fact that processor speeds would increase and memory speeds would increase in the future. And so when it came to doing things like the various accelerators that were built for the Apple II that eventually made their way into the Apple II GS and the Apple IIc Plus, they were sort of insane hacks as opposed to let's just speed things up like you were able to do on the IBM PCs. How well do Woz's video techniques translate to more modern display devices? Horribly, right? Woz's display trick was all about how can we sort of how can we fool the circuitry of a late 1970s color television into doing stuff it wasn't really intended to do. And as a result, about 50% of the time you hook up an Apple II to a modern flat panel or whatever, it befuddles the little chip in there that's going in and trying to take the analog video and trying to turn it into color. So it can just give up and say, I can't figure out what the colors these things are. The horizontal and vertical sync is just different enough where about half the time it can't be figured out. And I remember trying to record video from the Apple II on an 80s era VCR, and it was not too happy. It had a hard time. So very, very clever, but too clever in practice, which is true for a lot of Woz's designs.
Stephen got a couple more here. I'm not sure if you got these. Question is, does your columbia.edu site house most of this, or do you have another space online?
So the Columbia EDU site definitely has all of my stuff. For this video, I don't have much up there. I should put up some of the slides. I did I had a lot of fun and used, I don't know, 37 different tools or whatever to put together that video, and I've documented it a little bit. Let's see, were Woz's color and disc control considers hacks or innovations at the time they were originally released? Yes. They are absolutely hacks, and they were amazing that they were able to figure it out. Now, the one thing that's kind of interesting, and I should go back and check the prices at the time. So these hacks, these tricks that he played to reduce the cost, dramatically reduced Apple's manufacturing cost. But I don't think the other Steve passed much of that along to the users. And so that was one of the interesting things. And you have to go back and look at the cost of what Apple was selling its drives for versus Atari versus Commodore and so forth at the time. Woz did use stock stuff, but one, were they low cost, and did they have the same performance with others? So they did not have the same performance. There's no question that the video system on the Commodore 64, say, or on the Atari was more advanced, could do fancier stuff at the time. What was clear in putting together this presentation is that Apple really was started out of a garage, and you can really tell that. They did not have a lot of capital. And the big difference is that if you look at Atari and Commodore, they had capital that they could sink into designing these custom chips. Apple did not, and it did not. And its design reflects that. And so in some sense, it's sort of an oddity. The PET was a little bit closer, although still with the big physical design of it or what have you. But this is really the big thing. Now, when the Apple IIe came along, this is after Apple was much more established, they went the custom chip route because ultimately, if you can do custom chips, the per unit cost is much lower than using stock stuff. However, this was what Woz had to work with. This is what he knew how to work with, and this is what he produced.
I think another one came in. How similar, different is the Apple II to the original Apple I, particularly with regard to the circuitry reuse?
Yeah, so remarkably little. So from what I can tell, the Apple I and the Apple II, the commonalities were the 6502 processor, although you could substitute in a 6800 pretty easily. The video system was very, very different. So they both had more or less the same text display, but the way it was realized was just night and day different. So there's really not too much there is all. Yeah, Jobs was never much for passing on cost savings to the customer. Yeah, I think we have to do it. Oh, yeah. Even more fun is to record a TAR 2600 video on a VCR. Some of them don't get the line counts right. Yeah, I can't imagine trying to record 2600 video.
All
Or
right,
something like that.
Stephen. Thank you very much for that video and answering the questions. Unfortunately, running out of time, we have to move on to the next thing.